Let's talk about finding center of mass. Center of mass is just basically weighted averages based upon distance and mass. And if I have something in uniform density, and this can be shown with calculus, but ultimately if I have something with uniform density, the center of mass is smack dab in the middle. That's just going to make the rest of it a whole lot simpler. So if I have more than one, this is when the weighted averages pop in. The various steps are, I find the center of mass for each part, I establish an origin, and then I plug and chug. And this is my weighted average right here. I do position times mass for each of them. So the greater the mass, the more that term will have an effect or have an influence on it, and it will shift the total center of mass one way or the other. And then plug and chug. So take a look at a specific example. So if I have this block and this block where this is 4 kilogram mass and that's a 6 kilogram mass, this is 4 meters long and this is 2 meters wide, then the center of mass of the first one is 2 meters from the left edge. I'm establishing that as my origin, so that's 0. So it's 2 meters times 4 kilograms. So it's that distance times it's the position times the mass. And then it is the position of the second center of mass times that mass and divided by the total mass. So I end up with ultimately 38 over 10 or 3.8 meters. And so my center of mass is about there. That it is closer to this center of mass than that one because mass 2 has a bigger mass. Now if I chose a different origin, so if I chose my origin to be along here, now my position is negative 2 meters for the first one and 1 meter to the second one. So I have negative 2 meters times 4 kilograms because that's the mass here. 1 meter times 6 kilograms divided by the total mass, I end up with negative 0.2. So negative 0.2, if that's 0 right here, negative 0.2 sends me this way, which is 3.8 meters from the left-hand side. So I get the exact same answer as I had before. So let's generalize now. If I've got a whole bunch of masses, I do the exact same thing. I add up xi times mi, so the position in that particular direction, times the mass of that particular section, where this I is a value from 1 to however many parts I have, divided by the total mass. So if I break something up into an infinite number of pieces, then the mass of each piece becomes infinitesimally small. I'm not saying that the net mass is equal to 0, I'm saying it approaches 0. And so in this respect, the center of mass is just the integral of x dm. This is the infinitesimal mass, so in other words, m becomes dm. So the integral of x dm over the integral of dm, and this ultimately is just the total mass. All right, let's take a look at the situation where it is not as symmetric in both directions. So if I have a situation like this and I'm trying to find the center of mass presumably be somewhere along that line right there. But to find the center of mass of each part, come up with a coordinate axes. Don't necessarily have to have, it's not a line of origin, it's a two-dimensional problem, and then plug and chug, just as we did before. So in this particular case, where this is 3 meters long, 1.5 meters tall, and this is 2 meters wide and 4 meters tall, the center of mass of the first one, let's go back to it. So as we had this in the x direction, it's 1.5 meters this way, and from here to here, and in that direction, it is 4 meters. And so you can see in the math right here, it's 1.5 times the mass of the first bit, which is 7 kilograms, times 4 times the mass of the second part, divided by the total mass. And I end up with this value. So it was 3 meters wide and 1.5 meters tall. So in the x direction, just doing the x to start with, x, that it's 1.5 meters times 7 kilograms, because that's a 7 kilogram mass, and then 4 meters from here to here, and a 6 kilogram mass divided by the total mass, and end up with 2.6538 meters to the right, which is where it would be. So it's going to be just shy of the second block. And then when I look at the y values, I do that independently. So I now am going this way, and it is 0.75 meters up that way to the mass 1, and then mass 2, it is 2 meters. So I have 0.75 times 7 kilograms times 2 meters times 6 kilograms divided by the total mass, and I end up 1.3269. So I'm shy of going up there, so my final is somewhere around there, as shown right here. And I have x and y coordinates. I can generalize it by just saying that the radial position is just how far I go in the x direction, I hat, how far I go in the y direction, y hat, assuming I have I hat in the x direction and j hat in the y direction. So generalizing that, this was x center of mass, so let's sort of back up there. So that is the position of the center of mass, x center of mass I hat plus y center of mass j hat. And x center of mass is the formula I had on the other page. And again, this is total mass right there. And the sum of the y position times the mass divided by the total mass in the j hat direction. This is common to both of them, so I can just factor that out, and I'm left with whatever else I had there. So I'm left with this and this. This is x1 m1 I hat plus x2 m2 I hat plus and so on. And then the same thing over here. First object, second object, however many I've got. Now I'm going to sort it out by the object 1 and object 2. So I bring the 1's together, then I bring the 2's together, and so on. And then I factor mass 1 out, since it's common to all the first terms, and mass 2 out of the second terms. And so now I have 1 over the total mass is equal to m1 times r1 hat, because that is just the radial position vector. So m1 r1 plus m2 r2, and so on. In other words, I'm adding up all the mi ri's. So I can generalize my formula as the position of the center of mass is equal to the integral of r dm over dm. And again, this is just going to equal the total mass. And there's the center of mass.